This lesson begins our treatment of acids and bases, a subject that's central to a lot of chemistry. Our learning goals will include identifying acids and bases and the essential ingredients of an acid-base reaction, something that will be very handy in the lessons to come. So what are acids and bases? Well, they've been known since ancient times, but in ancient times they were defined by their taste or by particular reactions they undertook. For example, acids were things that tasted sour and bases were things that tasted bitter. This is a rule of thumb that we don't like to test these days because you never know what effect something's going to have on your health. Nevertheless, this is how the ancients defined acids and bases. More recently, Arrhenius, a Swedish chemist, talked about how acids can generate H+ ions in water, whereas bases generate OH- ions in water. It turned out that this characterization is actually pretty good, but it's overly restrictive, and it prevents us from defining certain things as acids and bases that probably really are. A much better definition was advanced in the 1920s by a pair of chemists, Bronsted-Lowry, and in effect what they characterized acids are as proton donors. We'll talk about what that means in the coming lessons, but a proton is basically just an H+ ion. If you think about hydrogen atom, it's a proton and an electron. If you remove the electron, all you have left is a proton, so we refer to it as a proton. A base then would be a proton acceptor. So the way one might diagram this is if we had two species, and I'll just generally label them as A attached to a hydrogen and B with a pair of non-bonding electrons attached to it, that the AH is an acid and the B with a pair of electrons is a base. So what happens in this sort of setup is that the AH loses H+, and that goes over to the base. Now, a better way to think of this is proposed by Lewis, and he basically defined base as an electron donor and acid as an electron acceptor. It's really the same general actions that are taking place in the Bronsted-Lowry definition, but if we follow the electrons, it makes a little bit better sense. The electrons on the base get moved over to form a bond to the hydrogen, which gives up the bonding electrons to A, and then we end up with an A- and an Hb+. Now, while Lewis's definition may make better sense in terms of what actually happens, it turns out the Bronsted-Lowry one is a little bit easier to use because it's easier to track where the proton goes. So we're going to use the Bronsted-Lowry throughout this module when we talk about acid-base chemistry. Now, when we start with an acid and it gives up its proton, we'll end up with a negative ion, which we will call the conjugate base to the acid HA. So in other words, there's a relationship between the acid HA and the ion A-, and that relationship is whether or not there's an H+ available. So for example, benzoic acid is an organic acid, and I've labeled the hydrogen that gets lost as an acid on the benzoic acid. When it loses that proton, it becomes the benzoate ion, which is the conjugate base to benzoic acid. So what I want you to be able to do is to recognize when you have a conjugate base for a given acid, the only difference between the two species is going to be whether or not it has an H+ attached or not. Similarly, we can draw this distinction for bases. A base would have a conjugate acid, and that will end up being the thing to which a proton is attached. So BH+ that was created in the Lewis picture is the conjugate acid to the base B with a pair of non-bonding electrons. A good example of that would be aniline, where we've got a non-bonding pair of electrons on the nitrogen. That's part of the amine group in aniline. And when that becomes protonated, then we have the conjugate acid to aniline. Now let's talk about acid-base reactions because that's going to be the central topic of this module. In an earlier example, we saw neutralization reactions, which basically are when an acid and a base come together and form water and a salt. There's a more general form that we can ascribe to acid-base reactions. It looks something like this, where we're going to have an acid reacting with a base, and the result of that reaction is going to be the conjugate base to the acid and the conjugate acid to the base. Now, in general in this module, I'm going to try to label acids in red and bases in blue. Bases in blue because they both start with B. However, in this case, I'm continuing to label the conjugate base in red just because I want you to associate the conjugate base comes from the acid and the conjugate acid comes from the base. So we can recognize these interactions. We look for the thing that donates the proton, that's the acid. The thing that accepts the proton is the base. Once the proton has been lost, that is the conjugate base. And once the proton has been added, that's the conjugate acid. Now, one other thing I need to mention, and that is that there are some species that can behave as both an acid and a base depending upon the situation. We call these amphoteric species, so they can be either an acid or a base. And the best example of this is actually something as simple as water. For example, here's a reaction where water and the methoxide ion react, and the water gives up a proton. It donates a proton to the methoxide ion to form methanol, and we end up with hydroxide and methanol. In this case, water is serving as an acid. It is donating its proton to the methoxide. We can also see water, though, react with something like HBr, in which case the proton is transferred from HBr to the water to form the hydronium ion, H3O+. So the thing that's the acid here is the hydrogen bromide, and the water is in fact acting as a base. All right, so the trick to acid-base reactions is finding the proton, finding where it starts and where it ends, and if you can find those things, you should be able to label your acid, your base, your conjugate acid, and your conjugate base.